the universe is tearing itself apart. Right now, as you read this, space itself is stretching, accelerating galaxies away from each other at speeds that defy everything we thought we knew about gravity and physics. Something is pushing the cosmos outward with unimaginable force, and we have no idea what it is. In 1998, two teams of astronomers made a discovery so shocking that it fundamentally rewrote our understanding of reality. They were studying distant stellar explosions billions of light-years away, expecting to measure how much gravity was slowing the universe's expansion. Instead, they found the opposite. The expansion wasn't slowing down. It was speeding up. This finding was so unexpected, so contrary to basic physics, that the teams initially thought they'd made an error. They checked their calculations repeatedly. They examined their instruments. They questioned their methods. But the data kept telling the same impossible story. The universe's expansion has been accelerating for the past 5 to 7 billion years, driven by something that shouldn't exist. Scientists called this mysterious force dark energy, and it now appears to make up roughly 70% of everything that exists. Not 70% of matter. 70% of all mass and energy in the entire cosmos. It permeates every cubic centimeter of space, exerting an outward pressure that overwhelms gravity itself on the largest scales. Think about that for a moment. We've identified the dominant component of our universe, the force determining its ultimate fate, and we fundamentally don't understand what it is. It's as if you discovered that 70% of your own body was made of something you'd never seen before and couldn't explain. The density of dark energy is astonishingly low, approximately 7 times 10 to the negative 30th grams per cubic centimeter. That's far less dense than the air you're breathing, less dense than the best vacuum we can create in laboratories. Yet because it's distributed uniformly throughout all of space, its cumulative effect dominates everything else. When Einstein developed his theory of general relativity in 1915, he encountered an unexpected problem. His equations predicted that the universe should either be expanding or contracting. It couldn't just sit still. But at the time, everyone assumed the cosmos was static and eternal, unchanging across time. Einstein found this prediction so troubling that he added a mathematical term to his equations, something he called the cosmological constant, specifically designed to counteract gravity and keep the universe stable. He later called this his greatest blunder. In 1929, Edwin Hubble discovered that distant galaxies were indeed moving away from us, proving the universe was expanding after all. Einstein abandoned his cosmological constant, seemingly closing that chapter of physics forever. Except the story didn't end there. 7 decades later, when astronomers discovered accelerating expansion, they realized Einstein's discarded constant might have been right all along, just for entirely the wrong reasons. The cosmological constant could represent a fundamental property of empty space itself, a baseline energy level that pushes outward against gravity's inward pull. But here's where things get truly strange. When physicists try to calculate what this vacuum energy should be using quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 120. That's not a small error. That's not even a large error. It's been called the worst theoretical prediction in the history of physics. Imagine trying to calculate the distance from Earth to the Moon and being off by not just millions of kilometers, but by a number larger than the entire observable universe raised to absurd powers. That's the scale of disagreement between our quantum theories and what we actually observe. Something is profoundly wrong with our understanding, either of quantum mechanics, gravity, or the nature of space itself. The discovery of dark energy came through studying type Ia supernovae, stellar explosions that serve as cosmic lighthouses. These particular supernovae occur when a white dwarf star accumulates enough mass from a companion star to trigger a thermonuclear explosion. Because the critical mass is nearly identical for all white dwarfs, these explosions have remarkably consistent brightness. Any remaining variations can be calibrated out using their light curves. This consistency makes Type Ia supernovae perfect standard candles. When astronomers observe one of these explosions, they can calculate its distance by comparing how bright it appears versus how bright it actually is. It's the same principle that lets you estimate how far away a streetlight is based on how dim it looks, except these stellar explosions are so luminous they can briefly outshine entire galaxies. In the mid-1990s, two competing teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were racing to map the expansion history of the universe using these distant explosions. Both groups expected to measure how much the expansion was decelerating. The question wasn't whether gravity was slowing things down, but by how much. The teams observed supernovae billions of light-years away, looking back through time to when the universe was younger. Based on their distances and redshifts, these ancient explosions should have appeared brighter than predicted if the expansion was slowing. Instead, they appeared dimmer. They were farther away than they should have been. The only way to explain this was if the universe's expansion had actually accelerated over cosmic time, pushing those distant galaxies farther away than simple momentum would allow. Space itself was growing at an increasing rate, driven by something completely unexpected. The scientific community initially met these results with skepticism. Extraordinary claims require extraordinary evidence, and this was about as extraordinary as it gets. But as more data accumulated, as different teams confirmed the observations using independent methods, the conclusion became inescapable. The 2011 Nobel Prize in Physics went to Saul Perlmutter, Brian Schmidt, and Adam Rees for their leadership in this discovery. What followed was a revolution in cosmology. Scientists developed increasingly sophisticated ways to measure dark energy's influence across cosmic history. They examined how galaxies cluster together, studied subtle distortions in the shapes of distant galaxies caused by gravitational lensing, and analyzed ancient sound waves frozen into the distribution of matter throughout space. Between 2013 and 2019, the Dark Energy Survey used an extremely sensitive 570 megapixel camera mounted on a telescope in Chile to photograph an eighth of the entire sky. Over 758 nights of observation, they recorded information from 669 million galaxies stretching across billions of light-years. More than 400 scientists from 35 institutions in 7 countries collaborated to analyze this enormous dataset. In January 2026, the Dark Energy Survey released their most comprehensive results yet, combining 6 years of data from multiple independent techniques. They examined baryon acoustic oscillations, those frozen sound waves from the early universe. They studied Type Ia supernovae across vast distances. They analyzed how galaxies cluster together under gravity's influence. And they mapped weak gravitational lensing, the subtle bending of light by massive cosmic structures. These 4 completely different methods of probing dark energy all had to agree with each other. Any inconsistency would suggest systematic errors or flawed assumptions. Instead, the data aligned remarkably well, providing constraints on dark energy's properties that were more than twice as strong as previous measurements. But the results also revealed something unexpected. While the data mostly supported the standard cosmological model, where dark energy remains constant across time, there were hints of something more interesting. Some combinations of observations seem to favor a model where dark energy's influence actually changes over time. This possibility has grown stronger with additional data. In March 2025, the Dark Energy Spectroscopic Instrument, or DESI, released an analysis based on nearly 15 million galaxies and quasars observed over 3 years. When combined with other measurements, their data suggested that dark energy's density might be slowly decreasing as the universe ages. the statistical significance hasn't reached the gold standard threshold for a confirmed discovery yet. Different combinations of datasets show preference levels ranging from 2.8 to 4.2 sigma, where 5 sigma is considered definitive. A 3 sigma result has only a 0.3% chance of being a statistical fluke, substantial but not yet conclusive. Still, the possibility is tantalizing. If dark energy truly evolves over time rather than remaining constant, it would require completely rewriting our standard model of cosmology. The implications would be staggering, potentially connecting dark energy to other unsolved mysteries in physics. And there's more. The same recent data has led some researchers to an even more dramatic conclusion. According to new models that attempt to account for these observations, the universe might not expand forever after all. Instead, it could reach a maximum size in roughly 11 billion years, then begin contracting. This Big Crunch scenario represents a complete reversal of our predicted cosmic fate. Rather than growing ever colder and more diffuse until stars burn out and black holes evaporate, leaving nothing but isolated particles in an endless void, the universe could eventually collapse back in on itself. In about 20 billion years, according to these models, everything would compress back to a singular point. The evidence comes from careful analysis of how dark energy appears to be behaving across cosmic time. To fit the latest observations, researchers propose that dark energy might be related to a hypothetical particle with extremely low mass, one that acted like a cosmological constant early in the universe's history but whose effects have been changing. This adjustment pushes the underlying cosmological constant into negative territory, which would eventually cause contraction rather than eternal expansion. These findings remain controversial and require confirmation from additional observations. But they demonstrate how rapidly our understanding is evolving. What seemed settled just a few years ago, the idea of eternal accelerating expansion, now faces serious challenges from new data. The real story, though, goes deeper than just competing models or evolving theories. To understand what's really happening, we need to look at what these measurements actually tell us about the fabric of reality itself. The tension scientists are seeing isn't just about numbers disagreeing. It's about the universe behaving differently than the laws we've written down say it should. When you measure how strongly galaxies cluster together today and compare that to predictions based on the early universe, something doesn't add up. This discrepancy has a name, the S8 tension. Galaxies seem to be clustering less strongly than they should be, given what we know about conditions shortly after the Big Bang. Multiple independent surveys keep finding the same problem. At first, researchers suspected measurement errors, systematic biases in how telescopes collect data or how algorithms process images. But as techniques improved and different teams using different instruments kept arriving at similar conclusions, that explanation became harder to accept. The gap has actually widened with the most recent dark energy survey data. Not dramatically, but enough to make it clear this isn't going away. We're not yet at the point where we can definitively say the standard cosmological model is wrong, but we're getting uncomfortably close to that threshold. Here's what makes this particularly unsettling. The standard model, called lambda CDM, has been extraordinarily successful for decades. It predicted the cosmic microwave background's precise pattern before we measured it. It explained the large-scale distribution of galaxies across billions of light-years. It accounted for the abundance of light elements formed in the Big Bang. Getting one thing this consistently wrong while getting everything else right suggests we're missing something fundamental, not just making a small error. So what could explain it? One possibility is that dark energy isn't constant after all. If its strength has been changing over cosmic history, that would alter how structures grow and cluster. The early universe would have evolved under different dark energy conditions than the late universe, potentially resolving the discrepancy between predictions and observations. But there's another problem, equally persistent and perhaps even more troubling. It's called the Hubble tension, and it goes right to the heart of how fast the universe is expanding right now. Edwin Hubble discovered in the 1920s that galaxies are moving away from us, with more distant galaxies receding faster. This relationship between distance and recession velocity is described by the Hubble constant, a number that tells you the current expansion rate of the universe. Measure that number accurately, and you know how fast space itself is growing. The problem? Different measurement methods give different answers. When cosmologists use the cosmic microwave background and the standard model to calculate what the Hubble constant should be today, they get one value. When astronomers directly measure distances to galaxies using supernovae and other techniques, they get a higher value. The difference is small, only about 9%, but it's consistent and statistically significant. At first, this seemed like it might be a calibration issue. Maybe one method had a subtle systematic error that could be corrected. Years of careful work have only made the discrepancy stronger. Both sides have refined their measurements, checked their assumptions, and the gap remains. In fact, it's grown slightly more significant as the uncertainties have decreased. This isn't just an academic puzzle. The Hubble constant determines the age of the universe, the distance scale of the cosmos, and the entire timeline of cosmic evolution. Getting it wrong means our whole picture of how the universe has developed over nearly 14 billion years might be off. What's causing the tension? Nobody knows for certain. One possibility is that dark energy has been changing its behavior, accelerating the expansion more recently than the standard model predicts. Another is that there's extra radiation in the early universe that we haven't accounted for. Some researchers have proposed modifications to Einstein's gravity equations on cosmological scales. Or perhaps the answer lies in something called quintessence. Unlike the cosmological constant, which is truly constant everywhere and always, quintessence would be a dynamic field permeating space, changing over time. The name comes from the ancient concept of the fifth element, beyond earth, water, air, and fire. It represents a fundamentally different way of thinking about dark energy. In quintessence models, what we call dark energy isn't a property of empty space itself, but rather a field, similar in concept to the electromagnetic field or the Higgs field. This field has energy, and that energy drives cosmic acceleration. But unlike a cosmological constant, the field's energy density can vary. It could be stronger in some epochs, weaker in others. It might even change from place to place, though current models suggest it must be fairly uniform to avoid conflicting with observations. The advantage of quintessence is flexibility. It could potentially explain why dark energy has the particular strength it does today. Maybe we're just living in an era when this field happens to have a certain value, and in the past or future, it was or will be different. This removes some of the fine-tuning problems that plague the cosmological constant. But quintessence brings its own challenges. What kind of field would have the right properties? It would need to be incredibly light, barely interacting with ordinary matter, and yet somehow dominate the entire energy budget of the universe. No known particle or field in the standard model of particle physics fits these requirements. Quintessence would require entirely new physics. No evidence has confirmed quintessence yet. The hints of evolving dark energy from recent surveys could be explained by it, but they could also be statistical fluctuations or systematic errors that further data will resolve. The theory makes predictions that differ slightly from the cosmological constant, predicting marginally slower acceleration. Future observations might be able to distinguish between them definitively. Some physicists think the best evidence would come from even stranger effects. Quintessence might violate Einstein's equivalence principle, the idea that all forms of mass and energy respond identically to gravity. Or it might cause fundamental constants of nature, things like the strength of electromagnetic forces, to vary slightly over cosmic time. Detecting such variations would be revolutionary, but so far, none have been found. There's another radical alternative worth considering. What if dark energy doesn't exist at all? What if we've been misinterpreting the data, and the real explanation is that gravity itself works differently on cosmic scales than Einstein predicted? Modified gravity theories attempt this. They keep everything we know about physics on Earth, in the solar system, even in galaxies. But when you zoom out to scales of hundreds of millions of light-years or more, the equations change slightly. Add extra terms, introduce new fields that affect gravitational attraction, and suddenly you can reproduce cosmic acceleration without invoking mysterious dark energy. These theories face steep challenges. Einstein's general relativity has passed every test we've thrown at it for over a century. Solar system observations constrain gravity's behavior with incredible precision. Binary pulsars, pairs of dead stars orbiting each other, provide even more stringent tests. Modified gravity theories must match all these observations while also explaining cosmic acceleration. The detection of gravitational waves delivered a particularly strong blow to many modified gravity theories. In 2017, astronomers observed both gravitational waves and light from the same event, a collision between two neutron stars. The gravitational waves and electromagnetic radiation arrived within seconds of each other after traveling for 130 million years. This proved that gravity waves travel at the speed of light, exactly as Einstein predicted. Many modified gravity theories predicted different speeds, and that single observation ruled them out. Most professional cosmologists remain confident that dark energy is real and that modified gravity isn't the answer. The evidence is simply too strong, too consistent across multiple independent measurements. Dark energy explains not just cosmic acceleration but the cosmic microwave background, the distribution of galaxies, the growth of structure over time. No modified gravity theory matches observations with the same precision. But confidence isn't certainty. Science proceeds by testing assumptions, and the current tensions in cosmological data suggest our assumptions might need revision. Whether that means dark energy evolves, new particles exist, or gravity behaves unexpectedly remains unknown. What we do know is this: roughly 5 to 7 billion years ago, something changed. For the first half of the universe's existence, matter dominated. Gravity was winning, slowing cosmic expansion. Then dark energy took over. The transition happened because matter dilutes as space expands. Pack galaxies into a smaller volume, and their gravitational influence strengthens. Spread them out, and it weakens. But if dark energy is a cosmological constant, its density stays the same no matter how much space expands. Eventually, as matter thinned out, dark energy's steady push overcame gravity's weakening pull. That transition point marks a fundamental shift in cosmic evolution. Before it, matter could still collapse under its own gravity to form new structures. Galaxy clusters could assemble, dark matter halos could grow, cosmic web filaments could connect across space. After dark energy took over, large-scale structure formation essentially froze. The universe's future was set on a different course. Understanding what drives this acceleration requires looking at what dark energy actually might be. The most straightforward explanation involves something Einstein introduced over a century ago, then abandoned, then had vindicated decades after his death. In 1917, Einstein faced a problem. His newly completed general relativity equations predicted a dynamic universe, one that either expanded or contracted. But everyone at the time believed the cosmos was static, eternal, and unchanging. To force his equations to produce a static solution, Einstein added a term he called the cosmological constant, represented by the Greek letter lambda. This constant acted as a kind of anti-gravity, a repulsive force built into the fabric of space itself that could balance ordinary gravity's attractive pull. Einstein described it as empty space taking on the role of gravitating negative masses distributed throughout the universe. Not actual masses, but a property of space that pushed outward. The cosmological constant allowed him to construct the static universe model, satisfying the astronomical consensus of his era. Then Edwin Hubble discovered the universe was expanding. Galaxies were racing away from each other. The cosmos wasn't static after all. Einstein quickly abandoned his cosmological constant, reportedly calling it his greatest blunder. For the next 60 years, most physicists assumed the constant was exactly zero. Space had no inherent energy, no built-in push. The 1998 supernova observations changed everything. Cosmic expansion was accelerating, not slowing. Something was pushing space apart. Physicists dusted off Einstein's cosmological constant and realized it might not have been a blunder after all. If the constant had a small positive value, it would produce exactly the accelerating expansion observers were measuring. Here's what makes the cosmological constant so strange. It represents energy inherent to empty space itself. Not energy from particles, radiation, or fields moving through space, but energy that space possesses simply by existing. Expand a region of space to twice its volume, and you've doubled the amount of this vacuum energy it contains. The energy density stays constant even as the universe grows. This property distinguishes the cosmological constant from ordinary matter. Galaxies spread out as space expands, diluting their density. Radiation redshifts, losing energy as wavelengths stretch. But vacuum energy maintains constant density regardless of how much the universe expands. That's why it eventually dominates. Matter thins out over time while dark energy's influence remains steady. If dark energy is a cosmological constant, its equation of state, the relationship between its pressure and density, has a specific value. Physicists call this value W, and for a true cosmological constant, W equals -1 exactly. This negative pressure is what drives acceleration. Positive pressure would resist expansion. Zero pressure would have no effect. Negative pressure actively pushes space apart. The latest observations from the Dark Energy Survey and DESI probe this equation of state with unprecedented precision. Both surveys measure W across different epochs of cosmic history, testing whether it truly equals -1 at all times or whether it varies. The standard model predicts constant W. Alternative models allow it to evolve. Results from 6 years of Dark Energy Survey data, released in 2026, combine 4 independent measurement techniques. Type Ia supernovae provide direct distance measurements. Baryon acoustic oscillations act as a cosmic ruler imprinted in galaxy distributions. Galaxy clusters reveal how matter clumps under gravity's influence. Weak gravitational lensing maps dark matter through its effect on light from distant galaxies. Each technique probes dark energy differently. Supernovae trace expansion history directly by measuring distances to specific points in time. Baryon acoustic oscillations measure the scale of space at different eras. Galaxy clusters show how structure formation has been affected by dark energy's competition with gravity. Weak lensing reveals the total matter distribution, both visible and dark, shaped by billions of years of cosmic evolution. Combining all 4 probes yields constraints more than twice as strong as previous analyses. The data largely supports the standard cosmological constant model. Dark energy behaves as if its density has remained constant across billions of years of cosmic history. The universe expands in a way consistent with W equaling -1. But there's a catch. DESI data, spanning 15 million galaxies and quasars collected over 3 years, hints at something unexpected. When combined with cosmic microwave background measurements, supernova observations, and weak lensing data, the results suggest dark energy's density might be decreasing slowly over time. The statistical significance ranges from 2.8 to 4.2 sigma depending on which datasets are combined. That's strong, but not yet the 5 sigma gold standard required to claim a discovery. A 3 sigma result has only a 0.3% chance of being a statistical fluke, but that's not zero. If this hint proves real with additional data, it would transform our understanding. A cosmological constant can't change. It's literally constant. But a dynamic field permeating space could evolve. Physicists call such a field quintessence, a fifth fundamental force beyond gravity, electromagnetism, and the strong and weak nuclear forces. Quintessence models involve a field with potential energy that varies over time. Early in cosmic history, this field might have behaved differently than it does today. Its energy density could have been higher or lower. As the universe evolved, the field rolled down its potential energy curve like a ball rolling down a hill, changing the strength of its repulsive effect. This evolution could explain why dark energy has the particular value it does right now. Perhaps we're observing it during a specific phase of its evolution, a phase that happens to produce the acceleration we measure. Different epochs would have seen different behavior. The far future might see it change again. No evidence yet confirms quintessence exists. Current data can't definitively distinguish it from a cosmological constant. The hint from DESI is intriguing but not conclusive. More observations, better statistics, and tighter constraints are needed. But the possibility has profound implications. If dark energy evolves, the universe's fate becomes uncertain. A true cosmological constant leads to endless accelerating expansion. The cosmos grows forever, becoming ever colder, emptier, and darker. But evolving dark energy opens other possibilities. Its strength could decrease, slowing cosmic acceleration. Or it could increase, tearing apart galaxies, stars, eventually even atoms in a Big Rip scenario. Most dramatically, some recent analyses suggest dark energy could reverse sign entirely. Instead of pushing space apart, it could begin pulling space together. New models attempting to explain both the DESI hints and other cosmological tensions propose a hypothetical particle with extremely low mass. This particle would have acted like a cosmological constant early in cosmic history but changed behavior over time. Adjusting the model to fit latest observations from both the Dark Energy Survey in Chile and the Dark Energy Spectroscopic Instrument in Arizona pushes the underlying cosmological constant into negative territory. A negative cosmological constant doesn't drive expansion. It drives contraction. One researcher analyzing this data concludes the universe might continue expanding for roughly another 11 billion years before reaching maximum size. Then expansion would halt. Reverse. The cosmos would begin collapsing, contracting until everything falls back to a single point in about 20 billion years total. A big crunch, the opposite of the Big Bang. This scenario remains highly speculative. It requires dark energy to behave in ways we haven't observed. The statistical evidence isn't yet strong enough to overturn decades of measurements supporting a cosmological constant. But it demonstrates how recent observations are challenging fundamental assumptions about cosmic evolution. The two major surveys, located in opposite hemispheres, closely agree in their measurements. That agreement strengthens confidence that the observations are real, not instrumental artifacts. Both surveys independently hint at the same unexpected behavior in dark energy's evolution. The evidence sits there in the data streams from two hemispheres, observations from instruments separated by thousands of kilometers yet seeing nearly identical patterns. Independent confirmation of something unexpected. When completely separate teams using different equipment in different locations arrive at matching conclusions, systematic error becomes harder to blame. Yet confidence remains cautious. Statistical significance hasn't reached the threshold physicists demand for claiming discovery. A 3 sigma result means roughly 1 chance in 300 of being random noise. Compelling, but not definitive. Physics requires 5 sigma before declaring a discovery confirmed. 5 sigma means 1 chance in 3.5 million of being statistical accident. The DESI and dark energy survey measurements hover between 2.8 and 4.2 sigma depending on which datasets combine. Intriguing. Suggestive. Not conclusive. But here's what makes this moment different from past hints that faded. Multiple independent lines of evidence point in similar directions. The surveys agree. Different measurement techniques converge. And critically, the observations address existing problems in cosmology that have persisted for years. The S8 tension. The Hubble tension. Two separate discrepancies that have troubled cosmologists for over a decade. S8 measures how clumped matter is in today's universe. Theory predicts one value based on observations of the early cosmos. Direct measurements of today's universe give a different value. Galaxies cluster less strongly than predictions suggest they should. This gap has appeared in survey after survey. Different instruments, different analysis methods, same result. The universe today doesn't match what early universe observations predict. The Hubble tension involves the expansion rate itself. Two completely different measurement approaches yield different values for how fast space expands. Local measurements using supernovae give one number. Cosmic microwave background measurements give another. The discrepancy has grown more pronounced as both techniques improved. These aren't minor disagreements. They represent fundamental challenges to the standard cosmological model. A model that otherwise works extraordinarily well. Lambda-CDM, the standard model, succeeds brilliantly at explaining countless observations. The cosmic microwave background's detailed structure. The abundance of light elements formed in the Big Bang. The large-scale distribution of galaxies. The acceleration of expansion. With just a handful of parameters, lambda-CDM describes the universe's evolution across 13.8 billion years. An elegant framework that has withstood decades of testing. Yet these tensions persist. S8. Hubble constant. Both suggesting something might be incomplete in our understanding. Evolving dark energy offers potential resolution. If dark energy's density changed over time, it would alter predictions for structure formation. Different epochs would see different rates of cosmic acceleration. The transition from matter-dominated to dark energy-dominated expansion would occur differently than lambda-CDM predicts. This could explain why today's universe looks slightly different from early universe-based predictions. The clustering of matter, the expansion rate, both potentially affected by dark energy evolution. But introducing evolution creates its own problems. What mechanism drives the change? What determines the rate? Why does dark energy have the value it does right now rather than some vastly different value? These questions lead to deeper mysteries. The cosmological constant problem. The worst prediction in physics. Quantum field theory, our best understanding of fundamental physics, predicts vacuum energy should exist. Empty space isn't truly empty. Virtual particle pairs constantly appear and disappear, quantum fluctuations inherent to spacetime itself. These fluctuations carry energy. According to quantum mechanics, they should contribute to a background energy density permeating all space. According to Einstein's equations, this energy would affect cosmic expansion. Calculate the predicted value. The answer exceeds observations by 120 orders of magnitude. Not 120%. Not twice as much. 10 to the power of 120 times larger than measured. This discrepancy has been called the worst theoretical prediction ever made. Our best theories predict a universe that shouldn't exist in any recognizable form. Expansion so violent that no structures could form. Space torn apart faster than atoms could hold together. Yet here we are. Galaxies. Stars. Planets. Life. A universe that clearly didn't experience that catastrophic vacuum energy. Something cancels out nearly all of quantum field theory's predicted vacuum energy to 120 decimal places, leaving only the tiny residual we observe as dark energy. No known mechanism explains this cancellation. No symmetry principle. No fundamental law. Just an unexplained fine-tuning that allows the universe to exist in a form capable of supporting structure. Some physicists suggest we observe this value through selection bias. The anthropic principle. Only universes with appropriately small dark energy can form galaxies, stars, planets, and observers. We necessarily find ourselves in such a universe because no other type permits our existence. This explanation satisfies some researchers. Others find it deeply unsatisfying, more philosophy than physics. Alternative approaches exist. Modified gravity theories attempt to explain acceleration without introducing dark energy at all. Perhaps Einstein's equations need adjustment on cosmic scales. Maybe gravity behaves differently across billions of light-years than within solar systems. Dozens of modified gravity theories have been proposed. Each must explain not just cosmic acceleration but every other test of general relativity. Solar system observations. Binary pulsar timing. Gravitational wave detections. Most fail. The 2017 detection of gravitational waves from merging neutron stars, accompanied by electromagnetic signals, ruled out entire classes of modified gravity theories. The waves traveled at light speed across 130 million light-years, matching predictions from general relativity to extraordinary precision. This single observation eliminated many alternatives to dark energy, constraining theories that predicted different gravitational wave speeds. Yet some modified gravity frameworks survive. They remain possibilities, though most cosmologists consider them less likely than dark energy existing as a real physical entity. The evidence supporting dark energy's existence comes from multiple independent sources. Type Ia supernovae. Cosmic microwave background. Baryon acoustic oscillations. Weak gravitational lensing. Galaxy cluster abundances. Each technique probes different aspects of cosmic evolution. Each has different systematic uncertainties. Yet all point to the same conclusion: something with negative pressure drives accelerating expansion. The convergence of evidence makes dark energy's existence more certain than any single measurement could provide. It's the pattern across multiple independent observations that builds confidence, which returns us to the present moment. The hints of evolution. The potential for dark energy changing over cosmic time. If confirmed, this discovery would rank among the most important in physics. Not just refining our model, but fundamentally altering our understanding of the cosmos and its fate. A cosmological constant implies one future: endless acceleration. Galaxies beyond our local group eventually receding faster than light. The observable universe shrinking as distant objects disappear beyond an ever closer cosmic horizon. Stars burning out. Black holes evaporating. The universe approaching maximum entropy, a cold, empty void. Evolving dark energy permits other possibilities. Perhaps acceleration slows. Maybe it reverses. The universe could reach maximum size, then contract. A big crunch instead of endless expansion. The observational evidence remains ambiguous. More data needed. Better statistics required. Tighter constraints on systematic errors. But we stand at a moment where decades of observation, instrument development, and theoretical work converge on questions that determine cosmic destiny itself. The Dark Energy Spectroscopic Instrument sits atop Kitt Peak in Arizona, a robotic eye scanning the cosmos. Over 3 years, DESI mapped 15 million galaxies and quasars, each data point a measurement of cosmic expansion at different epochs. The instrument doesn't just count galaxies. It measures their redshifts with extraordinary precision, determining how fast they recede from us and therefore how much the universe has expanded since their light began its journey. DESI's results, released in March 2025, suggested something unexpected. When combined with cosmic microwave background data, supernova observations, and weak lensing measurements, the numbers pointed toward dark energy changing over time. Not dramatically. The evolution appears subtle, gradual, occurring over billions of years. But if real, this evolution fundamentally alters every prediction about cosmic fate. The statistical significance hovers between 2.8 and 4.2 sigma depending on which data combinations researchers analyze. A 3 sigma result has only a 0.3% chance of being statistical noise. Compelling, but not yet conclusive. Physics demands 5 sigma for discovery claims, a threshold representing odds of less than 1 in 3.5 million that the signal arose from random fluctuation. What does evolving dark energy mean? Picture the cosmological constant as a perfectly flat ocean, its level never changing regardless of tides or weather. Now imagine instead a sea whose depth slowly varies, rising in some eras, falling in others. That's evolving dark energy. The repulsive force driving acceleration isn't fixed but changes as the universe ages. DESI data hints that dark energy density decreases slightly over time. If confirmed, this matches theoretical models involving quintessence, a dynamic field permeating space. Unlike Einstein's cosmological constant, which remains truly constant everywhere and always, quintessence evolves based on its potential energy landscape. Think of a ball rolling down a hill. Its speed and position change as it descends. Quintessence behaves similarly, its influence on cosmic expansion varying as the field evolves through different states. This matters because evolution determines destiny. A cosmological constant guarantees one future, eternal acceleration. But quintessence permits alternatives. If the field weakens enough, acceleration could slow. Gravity might eventually overcome dark energy's push. The universe could reach maximum size then reverse course, contracting toward a big crunch. One researcher, analyzing the 2026 data from both DES and DESI, calculated specific timescales. According to this model, the universe continues expanding for roughly 11 billion years before reaching peak size. Then contraction begins. The collapse accelerates, crushing everything back to zero in about 20 billion years total from now. These calculations required adjusting the underlying physics. The researcher proposed a hypothetical particle with extremely low mass that acted like a cosmological constant early in cosmic history. Over time, this particle's influence changed, its effects diminishing gradually. This adjustment fit the latest observations while pushing the true cosmological constant into negative territory. Negative dark energy doesn't repel. It attracts, pulling space together rather than pushing it apart. The two observatories, positioned in opposite hemispheres, reached remarkably consistent conclusions. DES in Chile and DESI in Arizona, using different instruments and independent analysis pipelines, converged on similar results. This agreement strengthens confidence that systematic errors aren't creating false signals. When separate teams using different methods reach compatible conclusions, the findings gain credibility. Yet uncertainty remains. The Dark Energy Survey tested their complete 6-year dataset against two models. The standard lambda CDM model, where dark energy stays constant, and WCDM, where dark energy evolves over time. Their data aligned with both models almost equally well. The evolving model fit slightly better in some analyses, but not decisively. The difference wasn't large enough to definitively choose one explanation over the other. This ambiguity frustrates and excites cosmologists simultaneously. On one hand, we lack definitive proof of evolution. On the other hand, the hints are tantalizing enough to motivate massive observational campaigns. Future surveys will map even more galaxies with greater precision, tightening constraints until the truth emerges. Consider what's at stake. If dark energy truly evolves, the lambda CDM model that has successfully described cosmic evolution for decades requires fundamental revision. Not minor tweaking. Major reconstruction. Every prediction about structure formation, galaxy evolution, and cosmic destiny changes. Textbooks get rewritten. Theoretical frameworks get rebuilt from new foundations. The S8 tension adds another layer of mystery. Measurements from the early universe predict a specific level of matter clustering today. But observations show galaxies clustering less strongly than expected. Multiple independent surveys confirm this discrepancy. When DES added their latest data, the gap widened further, though not yet conclusively. This tension between early and late universe measurements suggests something's missing from our models. Perhaps dark energy interacts with dark matter in ways we haven't considered. Maybe gravity behaves slightly differently on cosmic scales than general relativity predicts. Or systematic errors in observations create false discrepancies that will resolve with better data. The Hubble tension presents a parallel puzzle. Different methods for measuring the universe's current expansion rate yield different values. Cosmic microwave background observations combined with lambda CDM give one number. Direct measurements using supernovae and other distance indicators give a higher number. This discrepancy has persisted and grown as measurements improved, suggesting it's not simply measurement error. Some cosmologists propose that evolving dark energy could resolve both tensions simultaneously. If dark energy's influence changed over cosmic history in specific ways, it might reconcile the conflicting measurements. But this remains speculative. No single model yet explains all observations with complete consistency. Meanwhile, alternative explanations persist. Modified gravity theories attempt to explain acceleration without invoking dark energy at all. Perhaps Einstein's equations need adjustment on cosmic scales. These theories face severe constraints. The 2017 detection of gravitational waves from merging neutron stars, accompanied by electromagnetic signals arriving simultaneously, ruled out many modified gravity proposals. The waves traveled at light speed across 130 million light-years, exactly as general relativity predicts. This single observation eliminated entire classes of alternatives. Yet some modified gravity frameworks survive those constraints. They remain possibilities, though most cosmologists consider them less likely than actual dark energy existing as a physical entity. The convergence of evidence from multiple independent sources, supernovae, baryon acoustic oscillations, weak lensing, cosmic microwave background, galaxy clusters, all pointing to the same conclusion makes dark energy's existence more certain than any single measurement could provide. The philosophical implications extend beyond physics. If dark energy evolves, it suggests the universe follows a more complex script than we imagined. Not a simple story of eternal expansion, but a narrative with acts and transitions. The cosmos had an era of matter domination when gravity shaped structure. Then, about 5 to 7 billion years ago, dark energy's influence surpassed matter's gravitational pull. The expansion started accelerating. We live in this acceleration epoch, watching galaxies recede ever faster. But if dark energy continues evolving, this epoch itself might be temporary. Another transition could await. Perhaps billions of years hence, dark energy weakens enough that gravity regains control. The acceleration slows, stops, reverses. Or maybe dark energy strengthens instead, ripping apart not just galaxy clusters but eventually galaxies, solar systems, planets, atoms themselves in a big rip scenario. These futures aren't equally likely. Current data favors either constant dark energy leading to endless expansion or slowly weakening dark energy potentially allowing eventual recollapse. The Big Rip requires dark energy strengthening over time, which observations don't currently support. But ruling out scenarios requires better measurements than we currently possess. What's needed? More data. Deeper surveys. Longer observation campaigns. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will survey hundreds of millions of galaxies, measuring their positions and properties with unprecedented precision. The European Space Agency's Euclid mission, already operational, maps the geometry of the universe by observing billions of galaxies. These missions will either confirm dark energy's evolution or constrain it so tightly that constant dark energy becomes the only viable explanation. Within the next decade, cosmology should have definitive answers about whether the repulsive force driving cosmic acceleration changes over time. The stakes couldn't be higher. We're not debating abstract theory but the ultimate fate of everything that exists. Every galaxy. Every star. Every planet. Every atom. The answer determines whether the universe expands forever into cold emptiness or eventually collapses back on itself. Whether cosmic evolution is a one-way journey or a cycle. Whether we live in an epoch that will last eternally or merely one act in a longer drama. Human civilization exists in a narrow window. We emerged recently enough that the universe still permits observation of distant galaxies. Wait a few billion more years and accelerating expansion will push most galaxies beyond our cosmic horizon, their light redshifted to undetectability. Future astronomers would observe a much lonelier cosmos, unable to see evidence of the vast universe beyond their local group. We're fortunate to live when and where we can ask these questions and potentially answer them. The Roman Space Telescope and Euclid represent just the beginning. Ground-based observatories continue pushing boundaries too. The Vera C. Rubin Observatory in Chile, with its 8.4-meter mirror and 3,200-megapixel camera, will survey the entire visible sky every few nights starting in 2025. Over 10 years, it'll catalog billions of galaxies, tracking how cosmic structure evolves. Each observation adds another data point to the map of dark energy's influence across space and time. These instruments share a common goal: measuring dark energy's equation of state parameter with unprecedented precision. That parameter, often written as W, describes the relationship between dark energy's pressure and density. A cosmological constant has W equal to -1, always and everywhere. Quintessence or other dynamic dark energy would have W values that differ from -1 and potentially change over time. Current measurements suggest W hovers near -1, but uncertainties remain large enough that evolution can't be ruled out. The next generation of surveys aims to shrink those error bars dramatically. If W truly equals -1 to high precision, dark energy is likely the cosmological constant Einstein accidentally predicted. If W deviates even slightly or changes with cosmic epoch, we're dealing with something more complex and potentially more interesting. Consider what precision measurements mean practically. Right now, observations constrain W to roughly -1 plus or minus 0.05. That uncertainty leaves room for significant evolution. Future surveys target uncertainties below 0.01. At that precision, even subtle deviations from a cosmological constant become detectable. The difference between constant dark energy and evolving dark energy isn't academic. It determines whether the cosmos follows a simple script or a more elaborate narrative with multiple acts. The technological challenges are immense. Measuring galaxy shapes accurately enough for weak lensing analysis requires exquisite control of optical distortions. Tracking supernovae across billions of light-years demands precise photometry and spectroscopy. Mapping baryon acoustic oscillations needs enormous galaxy samples with accurate distance measurements. Each technique has systematic errors that must be understood and minimized below statistical uncertainties. Yet despite these challenges, progress continues accelerating. The 2026 Dark Energy Survey results demonstrate what's possible when multiple probes combine. Including data from DESI, Roman, Euclid, and Rubin will multiply that power. By the early 2030s, cosmologists expect to know whether dark energy evolves with better than 99% confidence. What happens if dark energy does evolve? The implications cascade through cosmology. First, the Lambda-CDM model requires modification. That model has been cosmology's foundation for decades, explaining everything from the cosmic microwave background to large-scale structure. Finding it incomplete would be revolutionary, comparable to discovering quantum mechanics or relativity. Second, evolving dark energy demands explanation. Quintessence models exist, but they're not uniquely specified. Many different fields could produce similar observational signatures. Distinguishing between them requires additional measurements beyond just W. Looking for spatial variations in dark energy, searching for correlations between dark energy and matter clustering, testing whether fundamental constants change over time, these observations could reveal dark energy's deeper nature. Third, the universe's fate becomes genuinely uncertain again. The potential for eventual recollapse, the Big Crunch scenario, emerges from specific models where dark energy weakens sufficiently over time. Current observations showing hints of decreasing dark energy density fit this possibility, though they don't yet prove it. If dark energy continues weakening, gravity eventually regains control. The expansion slows, stops, reverses. The timeline for such recollapse depends on how quickly dark energy evolves. Some models suggest the universe reaches maximum size in about 11 billion years, then collapses to zero volume roughly 9 billion years after that. Those numbers aren't predictions but possibilities consistent with certain interpretations of recent data. They require confirmation before anyone should consider them likely. Alternatively, dark energy might strengthen rather than weaken. That scenario leads somewhere even stranger. As dark energy density increases, its gravitational repulsion grows. Eventually, that repulsion becomes strong enough to overcome not just cosmic expansion's deceleration but also local gravitational binding. Galaxy clusters get torn apart first. Then galaxies themselves. Then solar systems. Planets. Eventually, even atoms succumb to the expanding space between their nuclei. This Big Rip scenario sounds like science fiction, but it's mathematically possible if dark energy evolves in certain ways. Current observations don't favor the Big Rip. The hints of evolving dark energy suggest weakening, not strengthening. But the uncertainties remain large enough that multiple futures stay on the table. Endless expansion. Eventual recollapse. Catastrophic rip. Heat death. The cosmos provides clues, not certainties. Meanwhile, theoretical physicists continue wrestling with dark energy's fundamental nature. Why does vacuum energy have the value it does? Quantum field theory predicts vacuum energy about 10 to the power of 120 times larger than observed. That's not a small discrepancy. It's the worst mismatch between theory and observation in all of physics. Something profound must be wrong with either the calculation or our understanding of how vacuum energy couples to gravity. Some theorists suggest the cosmological constant is exactly zero, and what we observe as dark energy is something else entirely. Quintessence fields. Modifications to gravity. Effects from extra dimensions. Even the possibility that we're misinterpreting the data completely, and the universe isn't actually accelerating. That last option seems increasingly unlikely given the convergence of multiple independent observations, but science requires considering all possibilities. Others pursue anthropic explanations. Perhaps the vacuum energy's value isn't determined by fundamental physics but by environmental selection. In a multiverse with different vacuum energies in different regions, only those with values near what we observe would permit structure formation and life. We necessarily find ourselves in a universe with the right dark energy because we couldn't exist in universes where it's vastly different. This anthropic reasoning troubles many physicists who prefer explanations based on fundamental laws rather than selection effects. The coming decade will test these ideas. Not through philosophical argument but through observation. Every galaxy surveyed, every supernova measured, every lensing distortion catalogued adds information. Dark energy might remain mysterious, but it won't remain unmeasured. The universe is telling us its story. We're finally learning to listen carefully enough to hear the details. What's remarkable is how recently this entire field opened. In 1998, cosmologists thought they understood the universe's future. Expansion would continue forever, gradually slowing due to gravity but never stopping. Dark energy wasn't part of the picture. Now, just over 25 years later, it dominates our understanding of cosmic evolution. The universe is 70% dark energy by mass energy content. That's not a small correction to previous models. It's a complete restructuring of how we think about the cosmos. And we still don't know what it is. Dark energy could be vacuum energy, a fundamental property of space itself. It could be a field permeating the universe, slowly rolling down some potential landscape we don't yet understand. It could be a sign that Einstein's equations need modification at cosmic scales. Or it could be something entirely unanticipated that current theories haven't imagined. That uncertainty isn't a failure of science but a feature. We know what we don't know. We've identified a profound gap in understanding and we're systematically working to fill it. The observations are getting better. The theoretical frameworks are becoming more sophisticated. Slowly, through accumulation of evidence and refinement of models, the picture clarifies. By the time today's graduate students become senior researchers, dark energy might be understood as thoroughly as atoms or stars. Or it might remain mysterious, a reminder that the universe still holds secrets beyond our current grasp. Either way, we're living through a remarkable moment in cosmology. The questions we're asking touch the deepest aspects of physical reality. The answers, whatever they turn out to be, will reshape how humanity understands its place in the cosmos. The data keeps flowing in. Every night, telescopes across the globe point toward distant galaxies, measuring their light, tracking their positions, building an ever more detailed map of cosmic evolution. The Nancy Grace Roman Space Telescope will launch soon, joining Euclid already in orbit. The Vera C. Rubin Observatory has begun its decade-long survey. Together, these instruments will observe billions of galaxies with precision that would have seemed impossible a generation ago. Within 10 years, maybe less, we'll know. Not everything about dark energy, perhaps, but enough to answer the fundamental question. Does it evolve or remain constant? That single answer determines whether the universe expands forever or eventually collapses. Whether our current epoch represents cosmic evolution's final act or merely one chapter in a longer story, the weight of that question sits heavy with anyone who truly considers it. We're not debating abstract mathematics or arcane theory. We're asking what happens to everything that exists. Every star will one day burn out, that much is certain. But does the universe itself have an endpoint? Or does it continue growing, cooling, fading into infinite darkness? If dark energy is Einstein's cosmological constant, unchanging and eternal, then endless expansion awaits. Galaxies beyond our local group will eventually recede so quickly that their light can never reach us. Future civilizations, if any arise, will observe a much lonelier cosmos. They'll see only their own galaxy cluster, surrounded by darkness. The evidence of a vast universe beyond will have vanished, carried away by accelerating expansion beyond any possible observation. Stars will exhaust their fuel. White dwarfs will cool to black dwarfs. Neutron stars will slowly decay. Even black holes, those seemingly eternal objects, will eventually evaporate through Hawking radiation over timescales measured in Google years. The universe approaches maximum entropy, a state physicists call heat death. No energy gradients remain to power any process. No structure persists. Just isolated particles, infinitely separated, in an ever-expanding void. That's one future. Bleak perhaps, but at least knowable. We understand the physics well enough to trace this path billions and trillions of years forward. The timeline is clear. The endpoint is certain. But evolving dark energy permits alternatives. If it weakens over the next billions of years, gravity might eventually regain control. The acceleration could slow, then stop. Then reverse. Galaxies would begin falling back together. The cosmic web would contract. Everything would compress, temperatures rising as space itself shrinks. Eventually, matter would reach densities and temperatures approaching the Big Bang, but in reverse. A big crunch, annihilating everything in a final singularity. Recent observations hint at this possibility. Not prove it, but suggest it. The hints aren't yet strong enough to overturn decades of measurements supporting constant dark energy. But they're strong enough that serious researchers consider the scenario plausible. Some models suggest the universe reaches maximum size in about 11 billion years, then collapses over the following 9 billion years. Those numbers carry profound implications. 11 billion years sounds distant, but it's less than the universe's current age. We've already lived through more time than remains before potential reversal. Humanity exists closer to the Big Crunch than to the Big Bang in this scenario. Not that humanity will witness it. Our sun becomes a red giant in about 5 billion years, long before any potential recollapse. Earth becomes uninhabitable even sooner. Whatever descendants of current life survive by then, if any do, they'll be so different from us that calling them human stretches the meaning beyond recognition. They might have spread across the galaxy. They might have transcended biology entirely. Or they might have gone extinct, leaving no trace. But that's our fate, not the universe's. The cosmos continues regardless of whether any observers remain to witness it. The expansion proceeds according to physical law, not conscious intent. Dark energy, whatever it is, operates on scales and timescales that dwarf human existence. And that's what makes this moment so extraordinary. We exist in a narrow window when the universe permits asking these questions and potentially answering them. We've developed the technology to observe distant galaxies, measure cosmic expansion, detect subtle variations in dark energy's influence across billions of years. We've built the mathematical frameworks to interpret these observations, connecting data to fundamental theory. Previous generations couldn't have done this. The instruments didn't exist. The theoretical understanding hadn't developed. Future generations might find it impossible too, if accelerating expansion eventually pushes distant galaxies beyond observation. We live in perhaps the only era when intelligent life could fully map the cosmos and understand its fate. That realization should inspire urgency. Not panic, but purposeful action. Every observation matters. Every improvement in measurement precision brings us closer to understanding. The surveys running now, the missions launching soon, they're humanity's attempt to answer questions that might only be answerable for a limited time. What will we find? Nobody knows yet. The data remains ambiguous. The tensions persist. The hints of evolving dark energy could prove real or could fade with better measurements. The Big Crunch scenario might be correct or might be completely wrong. We're in that uncomfortable phase where we know enough to ask precise questions but not enough to answer them definitively. Science often works this way. Long periods of confusion and uncertainty punctuated by moments of clarity when enough evidence accumulates to tip the scales. We might be approaching such a moment with dark energy. The next decade could bring the breakthrough that settles fundamental questions about cosmic fate. Or it might bring more ambiguity, more tensions, more hints of unexpected complexity requiring even more sophisticated observations to resolve. Either way, we keep measuring. Keep calculating. Keep refining our understanding. Because this matters. Not just to cosmologists or physicists, but to anyone who wonders about humanity's place in the universe. We're not just passive observers of cosmic evolution. We're the universe becoming conscious of itself, asking where it came from and where it's going. Dark energy ensures the answer isn't simple. 70% of everything that exists, and we still can't say with certainty what it is. Whether it's vacuum energy, a dynamic field, a modification of gravity, or something we haven't imagined yet. Whether it stays constant or evolves. Whether it drives endless expansion or eventual collapse. But we're closing in on answers. The instruments are ready. The observations are underway. The data is accumulating. Within a decade, maybe sooner, we'll know whether dark energy evolves. That knowledge will determine which future awaits. Endless expansion into cold darkness. Or eventual recollapse into a final singularity. The universe is about to tell us which story it's actually telling. And we'll be listening.